All right, let's get started. Welcome back. I hope everybody enjoyed their Wednesday off. Couple just very, very brief announcements. Actually, not a couple, really just one. Well, I thought about it. The deadline for homework 2, I extended to Wednesday. Remember, I said it was supposed to be due on Monday, but we didn't finish what we needed to finish. We actually should finish most of that today. After today, you should be able to attack probably problems 1, 2, and 3, and maybe a little bit of 4, although 4 is a really short problem. After Monday, you'll be able to finish 4 and 5. 4 and 5 are actually pretty short problems, so they're really not the meat of the assignment. The meat of the assignment is 1, 2, and 3. Today what we're going to do is we're going to continue our discussion of transform sections, which is the stage 2 behavior, and then get into ultimate capacity, maximum nominal flexural capacity. You'll notice here on the board, I've got a series of strain profiles and stress profiles. They probably don't make a lot of sense right now, but they will here in a little bit. Some of the diagrams on the board are actually purposefully incomplete, and that'll become clear here in a little bit. Okay. So let's sort of recap where we're at. So let's go back to this. So we have a concrete beam. We're taking that beam and we're loading it, and we're increasing that load conceptually and asking ourselves, well, how is it responding? How is it going to behave under this load? And so we say, well, okay, it'll have uncracked behavior until we exceed the cracking moment. So uncracked behavior is just going to behave like any other beam that you learned about in Engineering 216. And it's going to, the tensile region is going to resist the load, the compression region is going to resist the load, and that's going to happen until you reach the cracking moment. When the tensile stress here, the worst case stress here hits FR. And so once that stress on the bottom of the beam, if it's in positive bending, once that stress hits FR, boom, the concrete cracks, and we're in stage 2 behavior. So if you look at your stress profile, for instance, in stage 2, up here we have concrete and compression and concrete and tension. Here in stage 2, yeah, the concrete's still doing fine in compression, but in tension it's gone because it's cracked, it's literally separated. And so that's what's going on in stage 2. We did a series of examples looking at stage 1 behavior, and it was sort of served as a refresher on how to compute moments of inertia, sigma equals my over I, just all that stuff. It might have been a while since you have done, and just to make sure we're back on the same page. And so then we get into stage 2 behavior. That's when the moment is well past the cracking moment. So in this scenario, we still have our strains here, which I'm going to explain all that here in a little bit today. But for our stresses, the concrete is experiencing compression, but in tension, the concrete's separated, and so the only thing that's resisting that tension is the steel. So we now have to start considering the steel. Now when you're using sigma equals my over I, that expression and that theory assumes that you have a beam that's made of one material. And that's obviously not the case here because we have a concrete beam with steel reinforcement. So what we have to do is we have to transform that steel into an equivalent lump of concrete. I actually don't really like this image here on the slide because this lump here should be in line there. So this should actually be a little bit lower, so that's all on the same line. Because that's the whole point. The steel has to be in the same area. Okay? And then we'll use that to transform and determine stresses accordingly. And so we had started this example. We hadn't quite finished it, so that's actually what I'd like to do today is go into bending stress computations and finishing out the moment of inertia calculation and whatnot with this problem. So we had a concrete beam. It's 12 inches wide. It's 20 inches tall. Its effective depth is 17 inches. So, there's a difference between the total height and the effective depth. And I'll go ahead and tell you that D term, the 17 inches, the D quantity is going to become incredibly more important in the next, for the remainder of the semester. We're going to care more about that effective depth than we are the overall height of the beam. It's 3,000 psi concrete. It has 3 number 9, so the area of steel is 3 square inches, and it is being subjected to a bending moment of 70 foot kips. Now, one of the first things that we did when we did our math is we said, okay, it's subjected to a bending moment of 70 foot-kips. Are we actually in stage 2 behavior? Has the beam cracked? And so it's a simple justification or a simple determination. You just compute your cracking moment. So we have this beam. Our modulus of rupture is 7.5 lambda squared of Fc prime, which was about 411 psi. Moment of inertia, gross moment of inertia is 8,000 inches to the fourth. Now I want you to keep that number in your head, that the gross moment of inertia is 8,000 inches to the fourth. Remember, that's how stiff the beam is before it has cracked, okay? So after it has cracked, we will compute a new moment of inertia, a moment of inertia of the cracked section. And if physics makes any sense, then the cracked moment of inertia should be smaller than the gross moment of inertia, because the beam is weaker since it has cracked. Y sub t, distance from the centroid to the very, 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 very bottom, so h over 2. And then our cracking moment ended up being about 27.4 kips. Now remember, we're putting about 70 foot-kips a moment on it, so this beam has definitely cracked. We're well past the cracking moment in stage 2. So in order to assess its cracked behavior, one of the first things we have to do is compute our modular ratio. So that's the ratio of the Young's modulus for steel. Remember, I want that number burned into the back of your head by the time you graduate from college, 29,000 KSI. And then your Young's modulus for concrete, which we estimate is 57,000 squared of Fc prime for normal weight concrete. And so that comes out to about 3122 KSI. And you can be a little loose with rounding here, because when you compute an n value, we always take it to the, round it to the nearest whole number. And so when we did the math, it came out to about 9.3, so we said we're just going to take n to be 9. In fact, if I give you normal, for instance, if I give you normal weight, 3 KSI concrete, you could just take n equals 9. You don't have to go through the math. In fact, if you do normal weight 4 KSI concrete, I'm going to tell you that n is 8. So you can, and you can, if you don't believe me, you can do the math and you'll see it comes out to round to be 8. Sound good? Now, here's where we left off. This is where things got a little interesting. So remember, we turn the steel into an effective lump of concrete. So if we had 3 square inches of steel, 3 square inches of steel, in order to replace that, we would need 27 square inches of concrete, because our modular ratio is 9, and 3 times 9 is 27. So we replace that with that effective lump of concrete, and then in order to determine where the centroid is, we're basically just using, area times moment arm, like a centroid, sum of AY, A times the moment arm. So we look here at our section and we say, okay, all of the area above the neutral axis must have the same moment contribution as the area below the neutral axis, right? So what's the area above the neutral axis? What's the area of that box? Well, it's 12 times x. And how far is the centroid of that box from our neutral axis? That's x over 2. Then below the neutral axis, we have this area, which is NAS, so NAS is 27, times the distance. How far is it from here to there? And from there, that's 17 minus x. And so you look at this expression, and we got to break out the quadratic formula. So A is 6, B is 27, C is negative 459, negative B plus or minus square root of B squared minus 4AC all over 2A. We got 2 values of x. One of them was negative, and so that value obviously doesn't make sense, because that would mean that the centroid is above the beam, which wouldn't really make sense for this configuration. And so x is 6.78 inches. That's a lot of talking. Is everybody sort of back up to speed? Because it's been like 4 days since we had done that, so I wanted to make sure everybody remembers where we're at. Okay. Now, we need to compute a moment of inertia with this, for this section. Now, if you remember, the formula that we used last time ultimately to compute a moment of inertia was I plus AD squared. Do y'all remember that? Now, when we set up our table, and it was kind of big because we had to figure out where the centroid is. But we don't have to figure out where the centroid here is because we know where it is. It's 6.78 inches from the top. So the table that I set up is actually going to be a bit smaller, so I just wanted you to be aware of that. We're going to have a shape. We're going to have an I naught. D then an I plus AD squared. So if you look at our last example, it looks like I'm missing columns, but with that last example, there were data points that I needed that I don't need here. Okay? So we're going to have a sum here, and so on and so forth. So it's going to be very similar to the problem that we did last time. Okay. Well, let me see if I can scroll up a bit so that we can kind of see the beam. That's good. I kind of want to see that. I want to be able to reference this image up here. But yeah, the last problem that we did, we had an A, a Y, and AY. We don't need any of that because we know where the centroid is. Okay. Now I'm computing the moment of inertia of that shape up there. Okay? And there's only two components to that shape. There's the concrete, and there's the steel. And the steel being this lump down here, okay? So I'm going to start filling in these columns. I'm actually going to do it in a little bit of a backwards order because I'm going to start with the simple terms and then make it a little more complicated. So let's start off with the areas because I think that's pretty simple, okay? What is the area of this box?
12 times x.
12 times x. And what's x?
6.78.
There we go. So this is 12 times 6.78. And so that comes out to be what?
81.36.
81.36. Do I have a second on that? Just making sure everybody's awake on this Friday that probably feels a little bit like a Monday for us.
Yes, I said it.
All right, there we go. Okay. Now, that is the area of the concrete. What's the area of the steel?
Is that not just 27?
Exactly right. It's just 27. See, not so bad. All right. Let's do the distances next. Okay. Now, how far is it? Let's take the concrete first. How far is it from the neutral axis to the center of the concrete blob up top? Like what would the formula be?
6.78 over 2.
Exactly right, x over 2. So 6.78 over 2 is, probably do that in my head, was that 3 and, that 39? Did I do that right? Okay. That's good. How about the steel? How far is it from the neutral axis to the center of the steel?
We have 17 minus x for that distance, and then half of x.
Well, we wouldn't need to go half of x because remember, the center this is all one lump quantity. This doesn't have a height. So from the top of the beam to the steel is 17. So if all we do is subtract that x, we go from the center of the beam or the centroid of the beam to where the steel
going
is.
to the neutral. Okay.
Yes.
So then it is.
Bless you. So it'd just be 17 minus 6.78.
Okay.
Now, what is that? Is that
10.22? Yeah.
10.22? Not too shabby, right? Okay. Next up, moment of inertia. Now, let's take the concrete first. We have a box that's 12 inches wide, and how tall is it? 6.78, or x, whatnot. So what's the moment of inertia that's 12 inches wide and x tall? 12 times x cubed over 12, right? bh cubed over 12. So 12 times 6.78 cubed over 12, and that equals what?
311.67.
311.67. Do I have a second on that? Everybody good? Okay. Now, the moment of inertia of steel. Well, in order to compute the moment of inertia of the steel, you would need dimensions for that box, right? You would need to know how wide it is and how tall it is. But here's the thing. I'm drawing it as a box just because it's convenient. It's not really a box. It's just a lumped area value at that location. It doesn't really have any dimensions. So if it doesn't have any dimensions, what would the moment of inertia be of that individual shape? Wouldn't be anything. It would be zero. Okay? The reason it contributes to the section as a whole is because what I'm adding up are these. I plus AD squared. So this is going to be 0 plus that times that squared. So it's definitely going to have a contribution, but that individual shape doesn't have an area because it's not, I'm drawing it as a rectangle, but it's not really a rectangle. It's just a lumped quantity at that particular point. So think like a lumped mass with no dimensions is not going to have an individual moment of inertia. Does that make sense? So now we've got I plus AD squared, so we can do that for each row. We'll say like 1 decimal place, just to keep it simple. Then I got the first row, so it'll be 311.67 plus 81.6 times 3.39 quantity squared. Anybody got an answer for me?
1,246.7.
Do I have a second on that?
Yep.
There might be a difference or two with some rounding, but I'm not really worried about that for our purposes. All right, and then the next one, 0 plus that times that squared. Anybody got a number for me? Somebody else, come on.
28, 20, 21.
2820.1. I have a second on that.
Yep.
All right, so add those two up, what do you get?
Oh, I just erased.
That's 8, that's 6, that's 6. Did I do that right? Bless you.
406.
Are we good?
Yeah.
So maybe what we could say then, if we wanted to round, is we could say that the crack moment of inertia is 4067 inches to the fourth. Like just round it. Now I told you to keep a number in the back of your head. What's the gross moment of inertia of this section? 8,000. So before this being cracked, it had a flexural stiffness measurement of 8,000 inches to the fourth. Now that it's cracked, that's dropped to 4,067. So does it make sense that the stiffness of the system dropped a good bit once it cracked, and it's been reflected by this. Like once it cracked, it's basically half as stiff as it was. Doesn't mean that the stiffness is 0. I mean, just because it cracked doesn't mean it still can't resist load. It's just a lot less stiff than it was. Everybody good? Okay. All right. Now, one thing I will go ahead and tell you later that we're going to look at is, so this isn't going to matter now, but I'll just show you for later. So here's a beam with a distributed load, right? Right? And so what's the moment diagram look like? Something like that? So if your cracking moment is, if this is like 70, right? And your cracking moment is, let's say, 30, then your cracking moment is probably going to occur about like right here and about right there. Does that make sense? So some of the beam is going to be cracked and some of it isn't. So you're going to have a beam that in all actuality kind of looks like this. You know, like this is the beam that's uncracked and this is the beam that's cracked. So later on, we're going to have to compute sort of an effective moment of inertia that represents the fact that some of the beam's cracked and some of it isn't. We don't have to worry about that now, but that'll become important when we try and make sure that the beams don't deflect too much, because some of the beam's cracked and some of it isn't, so our deflection limit has to use the right moment of inertia. Does that make sense? Everybody okay with that? Okay. All right. Now I'm going to copy this image over up here because I'm kind of lazy, but you don't have to. I'm going to go on to the next panel. So So continue. So remind me, we have a modular ratio value of, what was it? 9. What was our x value? 6.87? 7.8. And then our cracked moment of inertia was 4,067 inches to the fourth. And if I remember correctly, we put a bending moment on here of 70 foot kips, right? Now, 70 foot kips is 70,000 foot-pounds, or 840,000 inch-pounds, right? So we can convert that from foot kips to inch-pounds. You could just multiply by 12,000, but I just wanted that value up there. And remember, sigma equals my over I. So, therefore, if I want to find the compressive stress, now this isn't the same thing as FC prime. FC prime is when I go take the cylinder down to the lab and I break the cylinder, what's the maximum stress before it fails? This is, literally, if I put this moment on this beam, how much stress is there? So it's not a material property, it's the effects of this analysis. So, in order to determine this compressive stress, I'm going to have a fraction, okay? Now, on the bottom of that fraction, I'm going to have a moment of inertia, but because the beam is cracked, that's going to be the cracked moment of inertia, right? Now, I have a bending moment. Well, let me ask you this, what's y? Now, in the theory, y is the distance from the centroid to our point of interest. And so if we're looking at a beam that's being bent, we're talking about from the centroid, and for compression in this case, we're talking about from the centroid to the very tippy top of the beam, right? Okay. Now, how far is it from the centroid to the very tippy top? What's the symbol? Well, now x over 2 will get us to the middle of the concrete. I'm talking about from the centroid to the very top. It's just x, right? Because here's the centroid, and from here to there is x.
Oh, of the whole thing, not of the, okay.
Of the entire beam, yes. So we're going to have mx over our cracked moment of inertia. So that's going to be 840,000 inch-pounds. That's going to be 6.78 inches, and that's going to be 4,067 inches to the fourth. And so the compressive stress is going to be what? Erase this. We'll say just nearest whole number, just keep it simple. 1,400 even? Have a second on that?
Yep.
And now what are the units? This is a stress, remember? PSI. Okay. Now, that's the compressive stress. What about the tensile stress? Well, remember, all the concrete in tension is gone, right? There's no concrete below the neutral axis. I mean, it's physically there, but it's cracked. So the concrete isn't doing any good. So the tensile stress in the beam is really just the stress in the steel. There is no stress in the tensile stress in the concrete because the tensile stress in the concrete is 0. It's all gone. For the steel, however, we apply the same principle, but we have a little tweak we have to do in the end. But what do we have? So we have a fraction, we have the moment of inertia on the bottom, we have the moment up top, but then we have a distance. How far is it from the neutral axis to where the steel is? It's not x.
17 minus.
It's 17 minus x, okay? Now, There is one other thing that we have to do, and it might seem a little confusing. So we'll say 17 minus x, but there's one other thing we have to do. Now, remember, we converted the steel into an equivalent lump of concrete, right? Well, in order to compute the stress in the steel, we have to make up for that conversion. And we do that by multiplying this by n. We have to multiply this whole thing by n to convert it back to steel so that when we compute our stress, we're computing apples to apples. Well, actually, in this case, apples to oranges because the materials are different. So we have to go back and throw that n quantity in again. So this is going to be 9 times 840,000, 840, not 84, inch-pounds times 17 minus 6.78 all over 4067 inches to the fourth. And so this is going to be F tenths equals F steel equals what? We'll say nearest whole number. Remember that, and the reason we have to do that again, this theory assumes that the beam is made of one material. So we converted it to concrete in order to compute an effective moment of inertia. But now we got to go back and make sure that that we're applying the same property. All right, anybody got a number for me? Somebody hadn't said something. You're an engineer, so you didn't have your calculator out. See this? Watch.
He was consulting his colleagues.
You've written professional emails before.
18998.
18998. Do I have a second on that? And what are the units on that? PSI. Boom. Not too bad, right? Now, one other thing to remember. I've been saying before that this isn't the maximum load that a beam can experience. And I know you're like, wait a minute, the beam cracked. Isn't that it? Look at the numbers. What is the maximum compressive stress in the beam? It's 1400 PSI. But what's the maximum stress that the concrete can experience? Well, this is 3000 PSI concrete. It can handle, or 1400 PSI, I think I might have said 1400 PSI. So the beam is experiencing 1400 PSI, but the concrete itself can experience well above 1400 PSI. But what about steel? Regular old rebar, normal grade 60 rebar, it yields at 60,000 PSI. It's only experiencing about 19,000 PSI. So we're not done. We can experience, or this beam can withstand far more load before it's gone, okay? Does that make sense? All right, but before I move on, any questions? Okay, let's talk about that then. Let's talk about how much load a given concrete beam can experience before it fails. Now, in order to explain that, I want to show you something. Now, I ironically brought an ACI 318 guide. This is an old one. This is from like 2008, so it's certainly a little out of date. I want to show you something. Okay, I drew a little line on my book right here. Okay, see this? This is a flat line or a perpendicular line to the page. Okay, what I'm going to do is I'm going to take this book and I'm going to bend it. Now watch what happens when I bend it. Can you tell me something about the line? It tilted a bit, but it's still straight, right? What you're looking at is sort of a visual representation of the strain profile. How much this beam deformed when I subjected it to applied load. And so that's what I'm seeing here, here, and ultimately right here. No matter what stage of behavior we're in, we assume that the strain always behaves like that. In other words, here's it before I apply the load, and here's after. And it's still straight, and it's still perpendicular, and it's from the centroid. So like if you were to track the centroid wouldn't move at all, and as you got further away from the centroid, it deforms more and more. Make sense? Okay. Now what happens here? Well, in stage 1 behavior, we've got the concrete beam in compression on top and in tension on the bottom, and that's fine until we hit FR. Once we hit FR, everything below the neutral axis goes away. So the only thing I have is concrete in compression, and I've got this. Okay? All right. So that's fine, but what happens when we start getting towards the end? What happens when we start getting towards ultimate capacity land? Well, I want to go back a few slides, and I want to pull this up. Y'all remember that? This is the stress strain curve for concrete for various different compressive strengths. And so regardless of what compressive strength I'm talking about, that's about what our stress strain curve looks like for concrete, right? And this point right here, that's FC prime, right? Now remember, when you have a curve like this and you get to like this point right here, that's when the cylinder explodes or it's done, right? This is it. This is ultimate maximum capacity before this concrete cylinder is gone, right? This is it. This is as maximum capacity as you can get. So over here, if I still assume that my strain is like this, what I've got is, this is about what my strain profile is going to look like. I've got what this rounded compressive stress curve over here, and then I've got, let's draw it like that, some tensile curve right here. Does that make sense? Now how do we deal with that? It's kind of tough. Let's explore that a bit. So if we're talking, so let me go back here. So we're talking about stage 3. So let's just be clear. Here's our strain profile, right? Linear strain profile, just like the book over here. And for the stress, I've got concrete in compression, which is very, very nonlinear, and I've got the steel in tension. Okay? Now, how do I deal with that? Well, let's go into that. I'm going to come back to this summary of concrete behavior in a second. I'm going to go back to that, but I want to look at this beam. I want to explore this. I want to go back to Engineering 216. I want to go back to basics, and I want to explore this beam, and I want to try and illustrate with this problem why this is such a challenge. I got a beam that's 12 inches wide, 20 inches tall, just like the problem we just did, right? Now I want to know how much moment is required to generate a bending stress of 8 KSI, okay? I got a beam, how much moment will generate a bending stress of 8 KSI? Well, there's actually a couple ways of doing that. The first way of doing that is sigma equals my over I, or just calculate and figure out a moment, right? So our sigma is 8 KSI, the moment of inertia, that's just BH cubed over 12. We just did that, 8,000 inches to the fourth. Y is H over 2, so plug and chug and you get that. So when you put that much moment on there, you get 8 KSI. Simple, right? Now that's one way of doing it. Here's another way of doing it. Here's my beam. Would you agree that my bending stress profile looks something like that? Now, let's go back to good old statics and centroids and whatnot. I'm going to integrate that. Now, what do I mean by integrate that? This is a moment, so we're talking about force times distance. So I'm going to integrate from right here. So let me see if my pen will cooperate. Let's look above the neutral axis. Okay, how far is it from the neutral axis to the center? Like that's going to be my moment arm. What is that? It's a triangle.
From there, isn't it 2/3?
2/3 of 10 inches, right? Remember that? So that's where this comes from. Okay? Force times moment arm. Okay? Now, what about the force? Well, what is the area of that triangle above the neutral axis? 1/2 of the base times the height. All right? Now, if I look at my units, 1/2 of this times that is only going to give me kips per inch. Remember, this bending stress profile occurs across the width. Oh God, my 3D art. So here's the beam. Here's that red dashed line. Really, the bending stress profile looks like that. Right? Going across the width, right? So, because it's, it's going to go like that. Please don't ask me to draw any better. That's about all I can do. I'm making it worse. So I'm going to have 1/2 of the base times the height, but then that's over the distance of 12 inches, right? So the force, 1/2 base times height over the beam width times the distance. Now, why do I have this 2 here? Because all that's from here. What about the one below? Well, it's the same. Same triangle, same distance. And so chug all this out, you get 6,400. Same answer. Okay? Sound good? Here's the problem. The problem is, how do we determine the area of that? Uh-oh, we have to break out the C word. A little bit of calculus. I know, calculus. This is, I think, the beginning and end of the calculus lecture in here, okay? I promise we're not going to use calculus in this. But I do want to show you a little bit of calculus to explain what we're going to do. Okay, so I have this nonlinear stress region that I need to integrate. I don't like nonlinear. I like boxes. Boxes have a length, a width. I know where the centroid is. It's simple, right? So I want to show you something. I want to consider the following graph. Okay, so I have the graph of y equals the square root of x, okay, and I've graphed that from 0 to 1, okay, and I've done that because this looks a whole lot like that, and it's simple. It's not some crazy, weird mathematical function. It's something contained and simple that I think we all understand. Y equals x to the 1/2 power, okay? Now what I want to do is, for this graph, I want to compute the area under the curve, and I want to compute the moment about the y-axis. And the area under the curve, I think everybody would get. The moment, that might be a little new to you. Now how do I compute the area under the curve? I'm asking you. How do I do that? Take the integral from 0 to 1, right? That's pretty simple. So if I integrate the square root of x from 0 to 1, and check it out, I get the area is 2/3. Okay, that's the area under the curve. Now that's the area. What about the moment? Okay, well, a moment is a force times a distance, or an area times a distance. So in calculus land, if the area is the integral of the function, the moment is the integral of x times the function. Okay? So I do a similar integral of, not the integral of the square root of x, but the integral of x times the square root of x. Okay? And so instead of it being x to the 1/2, it's the integral of x to the 3/2. So I continue that out, and I end up getting a moment of 2/5. Okay? I've got to believe, like, I'm going through the calculus pretty quickly. I'm not expecting you to sit here and chug out integrals. I'm just thinking you all follow along with what I'm doing here. Am I right? Okay. Now, I hate nonlinear. I don't like dealing with it. I like to avoid it. So my question for you is this. Can I come up with a box that has the same area and the same moment? Okay? Because I want to come up with something that has the same static principles. You know, what are our two fundamental equations of equilibrium? That the sum of forces equals 0 and the sum of moments equals 0, right? So I want to can I come up with something like this that possesses the same statical properties that this does? Because that is a whole lot easier to deal with than that. In other words, here's what I want to do. Here's my beam, can I take this weird nonlinear curve and replace it with a box? That's what I'm asking, okay? And that's what we're going to try and do. Now, what's the area of that box? Well, the area of that box is this x prime times this y prime. And the moment is the area of the box times the moment arm. And how far is it from here to the center of that box? Well, it's 1 minus half of that. Does that make sense? Sound good? So, I've got two equations, an equation for the area, an equation for the moment, and I've got two values. The area equals this, the moment equals that. So plug and chug them together, solve it out, and I get the following result. So x equals 4/5, y equals 5/6. So in other words, I want to look at that picture for a little while, make sure that that makes sense. I propose that what you're looking there on the slide are two figures that both have the same area under the curve and both have the same moment arm from, so both have the same moment from the x-axis. Does that make sense? Any questions on that? So I think what I want to convince you of is that it is possible to take something that's nonlinear and complicated and turn it into something that's a little bit easier to deal with. And notice the values, they're like 0.8, 0.83, stuff like that. Those values, or values like that, are going to become very, very familiar here in a second. Okay. If you understand that, then I want you to feast your eyes on this. This is the model that we use in concrete design to predict the maximum flexural capacity of a concrete beam. So we take this nonlinear compressive region and we convert it into this box. That's A tall and 0.85 FC prime wide. Okay? This is called the Whitney stress block approach. This approach has been in existence since the 30s. It's not going anywhere anytime soon. Okay? The idea is that instead of this, remember, this is FC prime. So remember, to create an equivalent box, we say that this is 0.85 FC prime. So the box has a width of 0.85 FC prime. It has a depth of A. And so you're going to see some terms here that are a little unfamiliar, like this term beta 1 and whatnot. It doesn't matter. Don't worry. We're going to delve into each of those terms in the next couple weeks. You really don't need to know about that right now. All you need to know right now is that we're going to assume that all of the concrete at its ultimate stage has a uniform stress of 0.85 FC prime. And the reason why we choose 0.85 FC prime is, again, it goes back to this, is that if the maximum value on this curve is like 100%, we can assume an equivalent box where it's about 0.8, 0.83. We go with 0.85. So we convert this into a box that has an equivalent stress of 0.85 FC prime and has a depth of A. And we use that to predict the flexural capacity. The steel that's in tension, remember, it is at its absolute maximum flexural capacity. So what we're going to do is assume that the steel has reached its yield stress. So the stress in the steel is Fy. So if you know the yield stress and you know the area, you can determine the force inside the steel as just As times Fy. Okay? Now the way that this works when you're analyzing a beam is you say, okay, the tensile force in the steel is the area times Fy. The compression is 0.85 FC prime times this. And so we set compression equal to tension because obviously we don't want the beam running away from us. We set those two equal to one another in order to determine where that depth needs to be such that C equals T, and then we sum moments. And that is it for maximum capacity. So of all of the three stages, I would argue that when it's all said and done, stage 3 is actually the easiest to compute. It's actually the easiest to determine and to do the math, okay? Everybody with me on that? Okay. Now, it's 10:45. I don't want to start this example now. What I will say is this, okay? You have a homework assignment that has 5 problems on it. Problems 1, 2, and 3 are easily the longer problems on the assignment. Problems 4 and 5 will take you very little time at all. They're really short, okay? And they cover flexural and nominal capacity. So we're going to hold on doing that. We'll cover that on Monday. This problem, again, it's going to be really quick. We have a beam that's 10 inches wide. It has an effective depth of 23 inches. Notice I didn't even give you the height. It's not going to matter for this problem. It's not even going to matter. We have 3 number 8s, so the area is 2.36 square inches. I got 4 KSI concrete, 60 KSI steel, and we're going to compute the flexural capacity. This is a really simple problem when you break it down. We're going to do this on Monday. With that, I know we're ending a couple minutes early, but that's pretty much all I got. So you folks that are not in steel, that's pretty much it. So I wish you a wonderful, wonderful weekend. We'll see you on Monday. That's all I got.